The article title is False Positive Identification in Intrusion Detection using XAI, which stands for Explainable Artificial Intelligence. Anomaly-based, which uses machine learning, has a great advantage over signature-based IDS. It can detect previously unknown attack, whose signature is not yet available. However, signature-based detection is still preferred in real-world implementations. Why does it happen? In a quick research, we see that many articles state that anomaly-based detection are more prone to false positives than signature-based detection. Furthermore, it is relatively easy to check if an alarm is false through signature analysis, but the same is not true for anomaly-based, where the only clue whether the alarm is true or not is the confidence of the detector. That explains why anomaly-based IDS is still a research topic, left aside in real production environments, where signature-based IDS is still the mainstream adoption. Our contribution is therefore to propose a method to post-process alarms from anomaly detection in order to identify those likely to be false more effectively compared to using solely the IDS confidence. Let's see how it works. In the first step, we define a confidence threshold, above which the non-existence of false positives is assumed. This procedure is done on the training set and confirmed on the validation set. The result of step 1 is a set of true and false positive alarms with low confidence, which in turn feeds the next step, where new attributes are extracted using two XAI techniques, adversarial approach and SHAP. Finally, these new attributes are used to train a second machine learning algorithm to detect false positives. This filter will then have a new confidence measure, which should be better than the confidence of the IDS. Thus, when the IDS operates in a production environment, all alarms generated with confidence below the established limit will be submitted to the false positive filter. To test the method's feasibility, we used a corrected version of CIC IDS 2017 dataset, together with an IDS powered by neural networks. Let's see the results. The test set is used to evaluate the method. First, we get the confusing matrix shown in the top left corner. Our goal is to efficiently identify as many of these 219 false positives as possible. In a production environment, they would be among the nearly 19,000 true positives. Using the threshold, a higher proportion of false alarms are selected, along with nearly 2,000 low-confidence true positives. This is called analysis set because analysts must manually inspect the samples to rule out false ones. If they cannot inspect the entire analysis set, it's more efficient to only analyze the parts that are likely to contain false positives. For this, we use the false positive filter. Let's see the final result in a graph. On the y-axis, we have the percentage of false positives where 100% equals 219 false positives in absolute values. On the x-axis, we have the analysis set percentage where 100% equals this sum, which is almost 2,500 samples in total. The entire analysis set is then sorted according to different confidence, represented by each of these lines. It is important to note that samples most likely to be false are ranked first. The blue line uses IDS confidence only, while the yellow and green use filters based on adversarial approach and SHAP respectively. The dashed line combines these two filters. The red line was obtained through the main idea present in the Petrie et al.'s work, which is to reuse the original attributes to train the false positive filter. If analysts can only inspect the low percentage of the analysis set, It is more efficient to use the proposed methods where higher percentages of false positives will be detected. Therefore, we conclude that explainable AI has the potential to overcome anomaly-based IDS problems, mainly the high false positive rate. Furthermore, explainable AI is a recent and still evolving research area, which can bring improvements to the proposed methods. Thanks for watching.